Okay, it's 11:35, so I will start. Hello everyone, we are moonsang and jieun from KT Cloud. Today, we are excited to share our journey of building a cloud service provider using Kubernetes and OpenStack. We will start with a brief introduction of our company, then move on to the platform, and finish with the products we've built. Our company, KT Cloud, is the very first public cloud provider in South Korea and currently the #1 data center operator in the country. In the cloud domain, we bring proven expertise in public and financial sectors, trusted technical capabilities, and strong scalabilities for multi-cloud and hybrid cloud environment. In the data center domain, KT Cloud operates 15 data centers across the nation, backed by more than 20 years of operational experience and AI-driven automation that ensures both stability and security. In short, KT Cloud has a leadership in both cloud and data center. And today, our talk will focus on the cloud side, specifically on building and operating a cloud service provider. Next is a new cloud-native platform initiative at KT Cloud. The goal is to re-architect our traditional, so-called classic cloud platform from the ground up. This time, built on open source technologies and network virtualization aligned with standard cloud architectures. But why did we have to move toward the next model? To answer that, we first need to look at the limitation of the traditional classic model. First, classic relied on a hardware-based tenant isolation model. Specifically, it depended on functions like VDOM tied to certain appliances. This approach had a fundamental scalability limit. Because the number of tenants was constrained by hardware, it became increasingly difficult to accommodate more customers as demand grew. Second, our classic cloud environment has been heavily dependent on vendor solutions. This can be led to vendor lock-in, which over time weakened our in-house technical capabilities. Even worse, the company's overall cloud strategy became tied to the roadmap of external vendors. Looking at just these two challenges, it becomes clear why we need to rethink and move toward the next model. So, how can we overcome the limitations of the traditional model I mentioned earlier? To address the first challenge, the hardware-based tenant isolation model, we transition to a cloud-native platform. By layering Neutron on top of OVN and OVS, and extending it to implement VPC, we were able to achieve tenant isolation at the virtualization layer. This approach successfully overcame the scalability limits of the old hardware-based isolation model. We will explain more about KT Cloud's VPC architecture in Chapter 4. Of course, before that, I will give you a proper introduction to the platform built on OVN, OVS, and OpenStack. The solution to the second issue, dependency on vendor solution, is to leverage and contribute to open source. From a company perspective, by leveraging open source projects built by global communities, we don't have to reinvent the wheel every time. This allows us to respond more agilely to a fast-changing market, maintain our internal technical expertise, and avoid being locked into any single vendor's roadmap. From a community perspective, simply consuming open source is not enough. Many companies take only what they need, but if we actively contribute, the story changes by fixing bugs, adding features, and sharing real-world use cases. We make the project healthier and stronger. This not only strengthens the ecosystem, but also accelerates the growth of our own engineers. Okay, in this and the following sections, I will introduce the structure of the foundation platform, which serves as the basis of the next project. It is composed of three main clusters: the admin cluster, the stack cluster, and the management cluster. So, why did we separate it into three clusters? There are two main reasons. First, let's talk about the separation of roles across our clusters. Each cluster has a clearly defined responsibility, and this separation is absolutely intentional, based on our operational policy. The admin cluster is in charge of managing and controlling the platform itself, and the stack cluster runs the actual OpenStack services and hosts customer resources. And finally, the management cluster takes care of all supporting applications and management services. Second, loose coupling. Even if one cluster experiences a failure or a resource conflict, the others remain unaffected. This is especially critical for the stack cluster, since customer resources must never be disrupted by external issues. Through this three-cluster architecture, the foundation platform achieves stability, scalability, and clear operational boundaries. Let me begin with the admin cluster. We call it the cluster of clusters because it is responsible for deploying and managing all the other clusters. For this purpose, we use Cluster API, which allows us to manage cluster lifecycle in a consistent and automated way. As many of you know, Cluster API is an open source project that standardizes cluster lifecycle management through a Kubernetes-style API. The admin cluster also plays the role of a giving tree. It acts as the central hub that provides everything the child cluster created via Cluster API need to operate. For example, it delivers Argo CD for GitOps-based deployment, Harbor as the container registry, and Vert for secure secret management. Next, let me introduce the stack cluster, which we can call the heart of the Next. This is where the OpenStack components run and where VMs are actually created on compute nodes. What makes the stack cluster unique is that OpenStack runs on top of Kubernetes. Even more importantly, the two platforms share a single OVS and OVN, which enables native communication between pods and VMs. In other words, workloads can be connected seamlessly, regardless of whether they run on a VM or inside a container. I will share more details about those use cases in the next section. Finally, let's take a look at the management cluster. We call this cluster the touchpoint with customers because this is where Kate Cloud's customer-facing services actually run. For example, the customer portal, IAM, VPC, and many of the core CSP features that customers directly use are all operated in the management clusters. Okay, in the previous section, we looked at the big picture blueprint of the foundation platform. In this section, we will shift our perspective and examine it from a networking point of view. Our main focus here is how we bring those clusters together to deliver cloud service as a CSP. Specifically, we will look at how OVN, OpenStack, and Kubernetes work together from a networking perspective to make that possible. The diagram illustrates the relationship among OpenStack, Kubernetes, and Kube OVN. What we've learned is that these technologies are not adopted in isolation, nor do they exist in a one-way relationship. Instead, they complement and reinforce each other, working together to realize a truly integrated cloud platform. So in this chapter, we will break down these relationships step by step, First, looking at OVN from the Kubernetes perspective, and then move from the OpenStack perspective. Let me start by explaining OVN. Many of you already be familiar with it, but in short, OVN is an open source network virtualization solution built on top of OVS. To put it simply, in the physical world, we use routers, switches, and hardware servers to build our physical networks. OVN allows us to achieve the same thing logically and virtually with our physical network devices, entirely through software. Now, let's take a quick look at the OVN architecture. Like most distributed systems, it follows a control plane and data plane model, and there are several components required to make this work. The control plane includes databases such as northbound and southbound. This layer is responsible for declaring, storing, and managing logical virtual networks. The data plane, on the other hand, is where the declared virtual networks are actually implemented. This consists of the OVN controller and OVS. The way it works is that each OVN controller deployed in a data plane communicates with the control plane, then applies flows to each managed OVS instances. Through this process, the logical network defined in the control plane are realized in practice within the data plane. Next, let's talk about kubeOVN. In one sentence, kubeOVN is a CNI plugin built on top of OVN. Its key characteristic is that it uses OVN as the backend to provide the networking functions required by Kubernetes. As we discussed earlier, OVN creates virtual networks, and in this case, the customer of those virtual networks are the Kubernetes pods. One of the main advantages here is that the networking feature provided natively by OVN can also be leveraged at the Kubernetes layer through kubeOVN. And perhaps the most important point, in order to function as a CNI plugin, kubeOVN is responsible for deploying and managing an OpenStack cluster itself. In other words, kubeOVN doesn't just connect Kubernetes to OVN. It actively runs and manages the OVN cluster as part of fulfilling its CNI role. Now, let's take a closer look at how kubeOVN deploys an OVN cluster. Put simply, the core components of OVN, the control plane and data plane, are packaged, deployed, and managed as pods in Kubernetes. Of course, these components still run as process on the host, just as in a native OVN deployment. The difference is that kubeOVN uses Kubernetes to orchestrate and manage these processes, grouping them into pods for lifecycle management. So, if we look at the single cluster from the networking point of view, it is deployed like this. Even when using kubeOVN, the fundamental OVN architecture remains the same. The control plane and data plane are simply implemented as pods. On the control node, kubeOVN deployed pods such as OVN Central, which provides the control plane functions of OVN. On the data plane, it deploys pods like OVN OVS, which handle packet forwarding and flow management. If we map this to the Kubernetes custom resource, it looks like this. On the left side, when we define a VPC custom resource in Kubernetes, it maps directly to an write OVN logical router. On the right side, when we create a subnet custom resource in Kubernetes, it corresponds to an write OVN logical switches on the backend. In short, left side shows what we declare in Kubernetes, and the right side shows how it's implemented in OVN. So, to summarize in one line, CubeOVN uses OVN as its backend and manages that OVN backend natively through Kubernetes to fulfill its role as a CNI plugin. Okay, next, let's shift to the OpenStack perspective on OVN. When we deploy Neutron on Kubernetes, we can set OVN as the backend driver. On the left side, you can see the Neutron configuration file. Notice the red box highlighting the path for the OVN northbound and southbound databases. Now, what are those IPs in reality? As shown on the right, they are actually the Kubernetes cluster IPs for the OVN northbound and southbound services. Okay, the key takeaway here is twofold. First, Neutron is using the same OVN backend, just like Kubernetes. And second, Neutron itself also runs as a pod, which means its communication with OVN is happening through the Kubernetes networking layer, specifically via service cluster IPs. Now, let's move one step further. Suppose we've already deployed Neutron, and then at the OpenStack level, we create logical resources such as a router or network, and finally launch a VM. What happens in this case? When Neutron creates a router or network, a corresponding logical resources is also created at the OVN level. If you look at the red boxes in the diagram, you will notice that the UUIDs match exactly, confirming the one-to-one mapping between Neutron's logical resources and OVN's logical entities. Going one step further, we can also see the Neutron router we just created is reflected all the way into CubeOVN's custom resources, specifically as a VPC. From this experiment, our key lesson learned is clear. The same OVN cluster deployed by CubeOVN is being shared and used by Neutron as well. To wrap up, here is the final summary. As shown in this diagram, the foundation platform is built in a way that shares the same network stack. By integrating the Kubernetes and OpenStack networking layer, we enable seamless communication between pods and VMs. This unified approach also lays the foundation for expansion into new services such as micro VM-based offering and beyond. Okay, next, jieun will introduce the Kate Cloud Next VPC, which has been built by applying these concepts in practice.
Thank you. Building on what was just explained, I will walk you through Next VPC, a service that puts our unified network foundation into practice. Let's start by looking at what services we, as a cloud service provider, aim to deliver to our customers. Through the Next project, KT Cloud set out to reach a global level of cloud capability by enhancing existing features and adding two new ones, VPC and observability. The VPC isn't just a network feature. It's a service-oriented network that lets customers design and control their own virtual networks. By offering it as an independent service, customers can now build infrastructure structure more flexible and autonomously. And today, I will begin with the most transformative part, the VPC. To empower customers to design and control their own networks, KT Cloud launches the VPC service. But why was this necessary? In the classic environment, KT Cloud used a VDOM model, separating only firewall policies on the shared network. Multiple customers shared the same physical network, so isolation, security, and scalability were limited. Customers couldn't define their own IP ranges or freely configure subnets, routers, and security groups. Next project solves these limitations by providing full network isolation and autonomy. Now, customers can build their own VPCs, define subnets and routers, and manage security policies directly. With an OVN-based management system, VPCs scale more flexible across cloud-native and hybrid environments. In short, VPC enables a fully independent, customizable private network for every customer. This diagram shows the core structure of KT Cloud's next VPC, designed to maximize security, isolation, scalability, and efficiency. Within each project, multiple VPCs operate as fully isolated network domains. Inside the VPC, subnets are divided across availability zones, each physically separated to ensure fault isolation and service continuity. As you can see in the bottom right diagram, the structure address scope to subnet pool to subnet ensures unique IP ranges and multi-tenant management without conflict. For example, within the address scope, there is a subnet pool which is then split into two subnets. For security, security groups protect instances, and Knuckles manages subnet private, creating multi-layer defense. NOT gateways let private instances access the internet securely, while internet gateways connect public-facing resources. In the classic environment, networks were shared with only firewall level separation. On the other hand, Next provides fully isolated VPCs with independent IP management, stronger security, and greater scalability. This slide shows the internal mapping of the next VPC architecture. It explains how components like project, VPCs, subnets, and routers are connected and organized. On the left, you can see the logical relationship between key elements. Each project can contain multiple VPCs, and each VPC connects to an address scope and subnet pool. This is part of the IP management layer, which defines IP policies and manages address blocks to ensure there are no overlapping ranges. The next part is the traffic layer, which includes the network and subnet components. This layer provides logical connectivity between instances within each availability zone. In other words, it defines how traffic flows inside the customer's VPC. At the bottom, the control layer manages communication between subnets and external connections through routers. Overall, the diagram on the left shows the logical mapping of these relationships, while the diagram on the right visualizes how these layers actually work together. From IP management to traffic flow to external routing. This layered design makes the entire network more modular, scalable, and easier to manage. Now let's see how the network actually works. To make it easier to understand, here's how it works in practice. Neutron defines the design, OVN implements it. For example, Neutron networks map to OVN logical switches, routers become logical routers, and subnets map to DHCP options. Ports connect as logical switch ports, and security groups are converted into OVN ACLs for constant policy control. Classic handled definitions separately from operations, but next project integrates both through OVN, unifying definition and execution, evolving into a fully automated overlay network. VPCs are isolated by design, but in real-world use, they often need to connect with other VPCs or the internet. That's how the VPC connects with the outside world. Let's take a closer look. This slide covers two key features for VPC interconnection. Peering allows direct, secure, private connectivity between VPCs. Route tables define traffic paths for peered or external network. In Classic, these connections were limited, but with Next allows multi-VPC traffic control that's both flexible and precise, giving customers full autonomy to design their network policies. Then let's look at external connectivity. The Internet Gateway connects public subnets directly to the Internet, while the NAT gateway lets private instances go securely without exposing internal resources. Classic had a single shared channel for all traffic, but Next VPC separates gateways for public and private control, improving security and clarity. Customers can now apply distinct security policies and manage all external access in an integrated way. We've seen how the VPC network is structured and how they connect across different environments. Then I will introduce other key improvements in next project. The first area is Next CI/CD. Before, each team had its own way of development. Some used Jenkins, other scripts or manual steps. Now we've unified everything into one constant CI/CD environment. This pipeline automates deployment and validation for both the OpenStack community version and KT Cloud services, making our release faster, safer, and more reliable. The second area is observability. We collect and integrate every metric, log, and trace across our system. Built on Grafana LGTM, it connects multiple open source tools and our in-house components to create a unified observability platform. By separating data for external users and internal admins, we ensure reliable data-driven services and clear visibility for both sides. Lastly, Next Console. This is the window where our customers experience all the power of Next. We redesigned it with a focus on usability, fixing pain points from the old Classic system and making it easier and faster for users to access everything they need. Together, these three components complete the foundation of Next, enabling us to build, monitor, and deliver cloud services efficiently. Let's wrap up with a quick summary of what we've achieved. Now, I'd like to share what's next for Next. We are bringing AI into our platform. We call it this AI on Next. On the software side, we are adding key AI features like GPU orchestration, scheduling, and AI-optimized storage. On the hardware side, we are moving from general-purpose servers to AI-optimized system, including DC racks, ARM CPUs, and DPUs. We are also deepening our core technology stack, expanding services like GPU as a service, bare metal as a service, and micro VM. There is still a long way to go, but we are moving forward one step at a time with confidence. If you have any questions, please feel free to email me. Thank you so much for listening.